If a rocket launched today carrying the first humans to Mars, most of them would be dead within a year, and almost nobody talks about why. Not because of some dramatic explosion, not because of an alien encounter, but because of radiation, bone loss, starvation, suffocation, and the simple crushing weight of isolation 94 million miles from home. Mars is not a red desert waiting for a flag. Mars is trying to kill you from the moment you leave Earth's atmosphere until the moment, if you're lucky, you return. And yet, for the first time in human history, we actually have a real plan to survive there. Not science fiction, not a fantasy sketched on a napkin. An actual, engineering-backed, physics-tested plan involving rockets already built, technology already tested, and timelines that are no longer decades away but years away. This is the full plan. From the moment you strap into a seat on Earth to the moment you could, theoretically, grow your own food under a red sky. Stay with me, because by the end of this you will understand exactly what it takes for our species to become multiplanetary, and why so many brilliant people believe it's not a question of if, but when. Let's start with the most basic problem nobody thinks about. Mars is not next door. Depending on where Earth and Mars are in their orbits, the distance between the two planets ranges from about 34 million miles at their closest to over 250 million miles at their farthest. Because both planets are moving, you cannot just point a rocket at Mars and fire. You have to use something called a Hohmann transfer orbit, a fuel-efficient curved path that takes advantage of the relative motion of both planets. This only works during specific launch windows that open roughly every 26 months, when Earth and Mars align in just the right way. Miss that window, and you wait over 2 years for the next one. Using this method, a one-way trip to Mars takes somewhere between 6 and 9 months, depending on the spacecraft, the trajectory, and how much fuel you're willing to burn for speed. Newer propulsion concepts, including nuclear thermal engines and SpaceX's Starship architecture, aim to cut this down. But for now, plan on the better part of a year sealed inside a metal tube smaller than a studio apartment, with the same 3 or 4 people, in zero gravity, hurtling through the most hostile environment humans have ever attempted to cross. That environment is not empty. It is filled with radiation that Earth's atmosphere and magnetic field normally shield us from entirely. Once you leave low Earth orbit, you are exposed to 2 major radiation threats. The first is galactic cosmic radiation, a constant low-level bombardment of high-energy particles from outside our solar system. Particles so energetic they can pass straight through spacecraft walls and human tissue, damaging DNA at the cellular level. The second is solar particle events, sudden bursts of radiation from solar flares that can spike to lethal levels within hours. On Earth, we're protected by a magnetosphere generated by our planet's molten iron core. Mars has no meaningful magnetic field, and space itself has none at all. A 6 to 9 month transit exposes astronauts to radiation levels that meaningfully increase lifetime cancer risk. And NASA's current safety standards are actually one of the biggest obstacles to approving long-duration missions. The proposed solution involves layered shielding, using water tanks, food supplies, and even human waste storage strategically positioned around crew sleeping quarters to absorb radiation, alongside real-time solar weather monitoring so the crew can retreat to a heavily shielded storm shelter section of the spacecraft if a solar event is detected. It's not perfect protection, it's damage control. While radiation attacks from the outside, your own body starts attacking itself from the inside, because human bodies evolved for gravity and space has none. Without the constant resistance of gravity, the human skeleton begins losing bone density at a rate of about 1 to 1.5% per month, a pace of bone loss that would take an elderly person on Earth roughly a full year to experience. Muscles atrophy rapidly, especially the muscles used for standing and walking, because in zero gravity, you never need them. Fluids that are normally pulled toward your legs by gravity instead shift toward your head and chest, causing facial puffiness, congestion, and increased pressure inside the skull, a condition now understood to potentially damage eyesight permanently in some astronauts. The heart, which no longer has to pump blood against gravity's pull, begins to weaken and change shape. To combat this, astronauts on long missions follow brutal daily exercise regimens, often exceeding 2 hours, using specialized resistance machines that simulate weightlifting in zero gravity, plus treadmills with harness systems to keep them tethered to a running surface. Even with this, by the time a crew arrives at Mars after 6 to 9 months in transit, they will be physically weaker than when they left, and they'll have to complete some of the most dangerous parts of the entire mission in that weakened state. That danger begins the moment the spacecraft hits the top of the Martian atmosphere, in a phase engineers grimly call entry, descent, and landing, or EDL. This is one of the hardest unsolved problems in all of space exploration, and here's why. Mars has an atmosphere, but it's thin, roughly 1% the density of Earth's. That's enough atmosphere to generate serious heat during entry, heat that can exceed 2,000 degrees Fahrenheit, but not enough atmosphere to slow a heavy spacecraft down using parachutes alone, the way we do on Earth. This creates what NASA engineers have nicknamed the 7 minutes of terror, the short window during which a spacecraft must decelerate from about 12,000 miles per hour down to a safe landing speed, using a precise combination of heat shields, supersonic parachutes, and retro rockets, all happening automatically because the communication delay between Mars and Earth, which ranges from about 4 to 24 minutes one way, makes real-time human control from Earth completely impossible. Every single landing attempt is a fully autonomous operation where the spacecraft's own computer makes every decision in real time. For robotic missions like the various NASA rovers, the mass involved is measured in a few thousand pounds. For a crewed mission carrying humans, habitats, and supplies, the mass involved could be dozens of tons, and no human mission has ever attempted a landing at that scale. This is why companies like SpaceX are testing massive vehicles like Starship, specifically for their ability to perform powered, propulsive landings using their own engines rather than parachutes, essentially flying the spacecraft down like a controlled rocket landing you'd see during a Falcon 9 booster return, except doing it in an atmosphere thin enough to make aerodynamic control extremely difficult. Assuming the landing succeeds, the very first decision that could determine whether the mission survives long-term is where exactly the crew touches down, because not all of Mars is created equal. The ideal landing site needs to satisfy several competing demands at once. It needs to be low enough in elevation that there's enough atmosphere above it to help slow a descending spacecraft, since higher elevation sites have even thinner atmospheric columns above them, making landing more dangerous. It needs to be close to the equator, where temperatures are the least extreme and solar power generation is the most efficient, since Mars's polar regions can plunge below -150 degrees Fahrenheit. But most importantly, it needs to be near accessible water ice, because water is the single most important resource for survival, more important than shelter, and in many ways more important than food. Regions like Arcadia Planitia and parts of Utopia Planitia have been identified through orbital radar and ground-penetrating instruments as having significant subsurface water ice at relatively shallow depths, sometimes just a few inches to a few feet below the surface. Some scientists have also proposed lava tubes, natural underground tunnels formed by ancient volcanic activity, as ideal shelter locations, since they provide a naturally formed rock ceiling that could offer substantial protection from both radiation and micrometeorite impacts, without requiring humans to build anything from scratch. Speaking of shelter, once you're on the surface, you need something to actually live inside, and Martian conditions rule out anything resembling a typical Earth structure. The surface temperature can swing more than 170 degrees Fahrenheit between day and night. The atmosphere is roughly 95% carbon dioxide, and is far too thin to breathe or to protect against radiation. Dust storms can occasionally grow to cover the entire planet for weeks at a time, blocking sunlight and coating everything in a fine, statically charged dust. Given all this, the leading habitat proposals fall into a few categories. The first is inflatable habitat modules, lightweight pressurized structures that launch compactly and expand once deployed, offering more livable volume per pound of launch mass compared to rigid structures. The second is regolith-based construction, using Mars's own soil, called regolith, combined with a binding agent and 3D printed using robotic construction systems that could theoretically arrive ahead of the crew and begin building shelter before humans ever set foot on the planet. This regolith shielding, when packed thick enough, roughly 3 to 6 feet depending on the material composition, can provide meaningful radiation protection, functioning similarly to how thick rock walls protect against radiation on Earth. The third approach, and the one many scientists consider the most promising for long-term habitation, involves using those pre-existing lava tubes as ready-made shelters, sealing off sections with inflatable airlocks and pressurized barriers, essentially turning a natural cave system into a livable colony without needing to build a structure capable of withstanding the surface environment directly. Now let's talk about the resource that makes or breaks everything: water. An average human needs roughly 2 to 3 liters of drinking water per day just to survive, and significantly more when you factor in hygiene, and especially when you factor in growing food. Hauling that much water from Earth for a long-term colony is not just expensive, it's physically impossible given current launch capabilities. This is why the discovery of widespread subsurface water ice on Mars fundamentally changed the entire colonization conversation. The plan involves extracting this ice through drilling and mining operations, then using specialized processing equipment to melt it, purify it, and convert a portion of it into breathable oxygen and rocket fuel through a process called electrolysis, which splits water molecules into hydrogen and oxygen using electrical current. This concept of manufacturing critical resources on site rather than transporting them from Earth is called in situ resource utilization, or ISRU, and it is arguably the single most important technological pillar of any realistic Mars survival plan. NASA already tested a scaled-down version of this concept with an instrument called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, which flew aboard the Perseverance rover and successfully demonstrated the ability to convert Martian atmospheric carbon dioxide directly into breathable oxygen, producing small but meaningful amounts during multiple successful test runs. Scale that process up to industrial size, and you have a system capable of producing not just breathing air for a crew, but also liquid oxygen for rocket propellant, meaning future missions might not need to carry enough fuel for the return trip at all, instead manufacturing it after they arrive. Breathing and drinking are only half the survival equation. You also have to eat, and shipping enough food from Earth to sustain a colony indefinitely is not sustainable past the earliest missions. This means any long-term Mars settlement needs to grow its own food, and Martian soil presents a serious obstacle here too, because Martian regolith contains compounds called perchlorates, which are toxic to humans and harmful to most plant life in high concentrations. Before regolith can be used for traditional soil-based agriculture, it likely needs to be treated to remove or neutralize these perchlorates, a process still being researched and refined. In the meantime, the more immediate and reliable solution is hydroponic and aeroponic farming, growing plants without soil at all, using nutrient-rich water solutions or nutrient mist directly on plant roots. Inside sealed, climate-controlled greenhouse modules where temperature, humidity, lighting, and carbon dioxide levels can all be precisely controlled regardless of what's happening outside. These systems have already been tested extensively aboard the International Space Station, where astronauts have successfully grown lettuce, radishes, and other crops in microgravity, proving the underlying technology works even in far more extreme conditions than a Martian greenhouse would face. Early Mars colonies will likely rely on a hybrid approach, combining shelf-stable freeze-dried food brought from Earth with a growing percentage of fresh, greenhouse-grown produce over time, gradually reducing dependence on Earth resupply missions as the colony's agricultural capacity expands. None of this, not life support, not water processing, not food production, not heating, not communication, works without a reliable source of power. And this is one of the most underappreciated challenges of the entire mission. Solar power is the obvious first choice, since Mars does receive sunlight, though at only about 43% the intensity Earth receives due to its greater distance from the sun. Solar panels can absolutely provide power, but they come with two serious drawbacks. First, Martian dust storms can block sunlight for extended periods, sometimes weeks, and dust accumulation on the panels themselves gradually reduces their efficiency over time unless regularly cleaned. Second, solar power simply stops working at night, which on Mars lasts roughly the same length as an Earth night, meaning any colony relying purely on solar needs substantial battery storage to survive the dark hours. Because of these limitations, many mission architects, including engineers at NASA, consider small nuclear fission reactors to be a more reliable long-term power source. NASA has already developed and successfully tested a compact fission reactor system called Kilopower, designed specifically for space and planetary surface applications, capable of providing consistent, weather-independent day and night power for years without refueling. A Mars colony would likely use a combination of both: solar arrays for supplemental daytime power, paired with one or more fission reactors as the reliable backbone, ensuring life support systems never go dark even during the worst dust storm the planet can produce. Surviving the environment is only one part of this puzzle. The human mind has to survive too, and this might be one of the most underestimated threats of the entire mission. Consider the psychological reality of a Mars crew. They are living in a small, enclosed space with the same 3 to 6 people for years, not months, factoring in transit time, surface operations, and the return journey. There's no stepping outside for fresh air without an hour-long process of donning a pressurized suit. There's no phone call home, because that 4 to 24-minute one-way communication delay means real-time conversation is impossible. Every message becomes a delayed exchange, more like a letter than a phone call. Isolation, confinement, and monotony of this scale have historically caused serious psychological strain even in far shorter and less remote conditions, such as Antarctic research stations, which are often used as the closest Earth-based analog for Mars mission psychology. Symptoms observed in these extreme isolation studies include depression, interpersonal conflict, decreased motivation, and a phenomenon researchers call the third quarter effect, a dip in morale and performance that tends to occur after the initial excitement fades, but before the return home feels close enough to provide motivation. Mission planners are addressing this through extensive crew psychological screening before selection, deliberately building diverse skill sets and compatible personalities into crew composition, providing virtual reality systems that can simulate natural environments like forests or beaches for mental relief, scheduling regular structured communication with family, and building meaningful work and personal autonomy into daily schedules so crew members feel a sense of purpose and control rather than helplessness. Now, even with the best psychological preparation, physical health emergencies on Mars carry a unique and terrifying weight because there is no evacuation option. If something goes seriously wrong physically, whether it's a broken bone, an infection, appendicitis, or a more serious medical event, there is no ambulance, no hospital, and no rescue mission that can arrive in time. Any mission this far from Earth needs to be almost entirely medically self-sufficient. This means crew members require cross-training in emergency medicine far beyond typical astronaut training, telemedicine support from doctors on Earth despite the communication delay, advanced diagnostic equipment that can function with minimal crew expertise, and a surprisingly sophisticated onboard pharmacy and surgical kit. Because even minor Earth-based medical issues can become life-threatening without proper intervention. Some proposals even include AI-assisted diagnostic tools designed to help a non-doctor crew member walk through emergency procedures step by step, essentially acting as a robotic medical assistant capable of guiding a colonist through anything from suturing a wound to potentially assisting with more advanced procedures in a worst-case scenario. Let's talk about who's actually planning to make this happen, because this isn't purely theoretical anymore. NASA's approach has generally been methodical and incremental, using the Artemis program's return to the Moon as a proving ground for many of the technologies Mars will require, including life support systems, habitat construction, and long-duration surface operations, before committing to the far riskier and more expensive step of sending humans to Mars directly. SpaceX, under Elon Musk, has taken a dramatically more aggressive posture, developing the fully reusable Starship vehicle specifically with Mars colonization as its stated primary purpose, aiming to eventually send large numbers of Starships in a single launch window carrying cargo, construction equipment, and eventually crews, with the explicit long-term goal of building a self-sustaining city on Mars, not just a small outpost. Whether the aggressive SpaceX timeline or the more cautious NASA timeline proves more accurate remains genuinely uncertain, and mission dates discussed publicly have shifted multiple times as engineering realities become clearer. What is clear is that, for the first time, the barrier to Mars is no longer primarily about whether the technology can theoretically exist. It's about refining, testing, and scaling technology that already exists in early or prototype form. There's also a longer-term dream sitting behind all of this practical engineering, and that's the idea of terraforming, the theoretical process of transforming Mars's environment over time to become more Earth-like, potentially thickening the atmosphere, raising the temperature, and eventually allowing liquid water and breathable air to exist on the surface without artificial habitats at all. Proposed methods have included releasing greenhouse gases to trap heat, redirecting asteroids composed of ice to impact the surface and deliver water and atmospheric material, or even theoretical orbital mirrors designed to focus additional sunlight onto the polar ice caps to trigger large-scale sublimation. However, there's a fundamental problem that terraforming discussions often gloss over, which is that Mars lacks a global magnetic field, meaning any atmosphere we did manage to build up would be gradually stripped away by solar wind over a long enough timescale. The same basic process scientists believe stripped away most of Mars's original atmosphere billions of years ago. This means true, permanent terraforming likely isn't achievable with current or near-future technology, and most serious mission planners treat it as a multi-generational, centuries-long aspiration, rather than any part of the practical plan for the first colonists, who will need to live inside sealed, engineered habitats regardless of any terraforming progress made in their lifetimes. So what does the realistic timeline actually look like when you strip away the hype and look at where the technology genuinely stands right now? The most immediate milestone is successful uncrewed cargo landings of large-scale vehicles like Starship, proving that heavy payloads can survive the entry, descent, and landing sequence intact. Following that, robotic ISRU demonstration missions would need to prove that oxygen, water, and fuel production can actually function at meaningful scale under real Martian conditions, not just in a lab simulation. Only after those milestones are convincingly achieved would a crewed mission become a responsible decision, both from an engineering standpoint and from the ethical standpoint of not sending humans to a location without a demonstrated working survival infrastructure already in place. Realistic estimates from within the space industry, factoring in the setbacks that have historically affected every major space program, tend to place the first crewed Mars landing sometime in the 2030s, with a small, evolving outpost potentially transitioning toward genuine self-sufficiency sometime in the following decades, assuming continuous funding, continuous political will, and no major catastrophic failures along the way. Here's the thing that I think gets lost in every conversation about Mars, whether it's framed with pure excitement or pure skepticism. This isn't really about Mars as a vacation destination or even as a scientific curiosity. It's about whether human civilization, and honestly human consciousness itself, exists on more than one planet at a time. Every species that has ever existed on Earth has eventually gone extinct, whether through asteroid impact, climate shift, or countless other causes we're still discovering in the geological record. Earth itself is not guaranteed to remain hospitable forever, and even setting aside worst-case scenarios, there's a simpler argument, which is that expanding beyond a single planet is how a civilization becomes genuinely resilient rather than fragile. Mars isn't a paradise. It's cold, it's irradiated, it's got a poisonous atmosphere, and it will require some of the most sophisticated engineering our species has ever attempted just to keep a handful of people alive on its surface. But for the first time, we have the actual pieces of the plan sitting in front of us, tested in labs, tested on the International Space Station, tested by rovers currently sitting on the Martian surface right now, and tested in the successful landings of increasingly capable robotic missions over the past several decades. The question isn't whether humans could theoretically survive on Mars anymore. The pieces of that answer already exist. The real question is whether we choose to put them together, and if the current pace of progress is any indication, we may find out sooner than most people realize.